Okay, so today's notes are titled Riemann Sums. And Riemann Sums, you could actually start by thinking of the most basic case, which you see two pictures illustrated up here. And what we've done, and you've actually done this in the past, in maybe a pre-algebra or geometry class, something like that, where you just try to find area underneath these two kind of boxy curves. And what you might do is separate them up into shapes that you know. So this first one's a square, this next one's a rectangle, and then you might add up basically the areas of each one of those shapes to get the total area underneath that curve. A similar process can be done with different shapes, but this would just give you the area underneath the curve. So what makes calculus a little bit interesting is these are not as boxy. These curves are very curvy, and finding area using rectangles here gets a little bit different. So let's say we wanted to find the area underneath these two different curves as best we could. Well, what you might do is start drawing, rectangles very similar here. This one's going to be a little weird. Maybe do a little rectangle here. All right, so as you can see, these rectangles aren't always that good. There's some error. So in these spots here, we have underestimated the area. Actually here as well. But in this spot, we've actually got an over approximation. So some of those errors are going to cancel, but this is not going to be exact. So this is going to be approximately the area here. And same thing here. You can draw your rectangles, differently, but that one's going to say be an over approximation. This one actually could be pretty good. This one maybe do an over approximation there, and there, another big rectangle there. So these rectangles, again, it's going to give you just an approximation. It's not going to be exact. Well, this process is actually called rectangular approximation method, and we'll be calling them Riemann sums. So you can see this picture on the right. There's some curve, and we have a starting and an ending point, so that's our interval from A to B, and we want to find that area in the shaded area there, and that looks like that would be perfect, all that area, and obviously that's not any sort of rectangle. So what we do is that we take this interval from A to B and we divide it up into something called subintervals, and then we can draw a rectangle at each one of those subintervals. So we divide this up however many times, and the problem will always tell you how many times to divide it up, and then you can see like we would basically make a bunch of rectangles to approximate this area. The distance, like right here between this x and that x, is like your base of the rectangle. The height going up, well, that's really the y value. So what you do is you use the function f of x, you plug in whatever x value you have to find the height, and the width of the rectangle is between two different x values, and we'll find that here in just a minute. So we're basically just using area formula, base times height, a bunch of times. So quick notation, we're going to talk about something called a left endpoint, which you might see abbreviated like this. A right endpoint would be RAM, and then there's a midpoint, which is abbreviated like this. So let's see a couple of those and what they look like. Here, in this first graph, we have, looks like 4 rectangles to try to approximate the area underneath this curve. And what you need to note is this is a left Riemann sum. So left, look like that. So why is it left? Because the left corner of each one of these rectangles is on the actual curve. The second one is not a right one, because if it was the right, then the right endpoint would be on the curve. This is a midpoint, because the middle of each rectangle is on the actual curve. And if you go down, you'll see that the width of these is 2, so the first one goes from 0 to 2. So at 1, the rectangle is going to be on the curve. At 3, rectangle at 5 and 7, so on. So now we need to talk about accuracy. Which one of these would give a better approximation? Well, in this first one, we have a lot of gap here. And the 3 that I just showed you there are under approximations. The curve actually has more area, but these rectangles have a lot less. So that's an under approximation for sure. But in this region right here, we've over approximated the area. We're over the curve. So some of that area is going to cancel. Now the interesting part about the midpoint is that each rectangle, there's an over and an under approximation. So in each rectangle, some of that area is going to cancel. So generally the midpoint is a more accurate approximation. So something to think about here is how would you find even a better approximation? How can I make this have less error? So be thinking about that. And that'll be something that we talk about next time. So here is the idea. This is the process. What you're going to do is you're going to take your interval, whatever it is. So in this case, we're going from 0 to 8. And you're going to divide it up into sub-intervals. So step 1, divide the interval into n sub-intervals. And it says n will be given. So in our example, there are 5 rectangles. So we're going to be dividing up into 5. And our dots are kind of already given on this graph. So we're actually going to divide that up like that. Now it says create n rectangles whose base equals the width of the subinterval and whose height is determined by the function value at the left, right, or midpoint. So looks like this problem says illustrate the left and the right endpoint on each graph below. So on the left one, let's do left endpoint. So it looks like my first interval goes from 0 to 2, my next one 2 to 4. This one seems smaller, so 4 to 5, then 5 to 6, and then from 6 to 8. So that's my width for every rectangle. Now I'm going to go up, but when do I stop going up? Well, this is going to be our left endpoint, so go to the left endpoint and go up until you hit the curve. Now there's your rectangle. Sorry, my rectangles are poorly drawn here. Same thing in the next one. Say if I went up, I'd hit the curve here, go straight across. The next one is a smaller rectangle, only with a 1. So left endpoint's right there. This left endpoint's down here. Again, small one. The next one is 2. Oops, whoa. Okay, so there we are. You've illustrated the left endpoint. Now if you look again at each one of those rectangles, the left endpoint is on the curve. So we're gonna do the same thing, but this time we're gonna do a right endpoint. So from 0 to 2, I'm gonna be at that point, and that determines the height of my rectangle. At 4, I'd be here. 5, I'm down here. 6, way up there. Okay, draw that. And then 8, right about there. Okay, so again, at each one of those rectangles, the right endpoint is on the curve. So we can look at those two different values. They'd probably be a little different, but they both would be an approximation for the area underneath that curve f of x. Okay, so what we have next is what you'd probably see in a traditional problem now. So here's the whole thing. Here is a quadratic, some parabola, and we're going to use 4 rectangles, remember that's always going to be given, to find the area under the curve from 1 to 3. Okay, so all I care about is 1 to 3. Don't care about any of that other part that you see on that graph. And then it says use left, right, and midpoint. So we're going to be doing all of this together here. And as you saw up here, the points were already kind of given for us. So this first rectangle has a width of 2. The second one has a width of 2. And these two have a width of 1. That one has a width of 2. So those are uneven, which is fine. But when you're doing your own, generally we have widths that are uniform. We have so there's a way of finding that. So I like to find the width with b minus a over n. So b is our ending of our interval, so that's 3. minus a, the beginning of our interval 1. And n is always the number of times you're dividing that up, so that's 4. So if you do the quick math, that's 2 over 4, or a half. That means each one of our widths is going to be a half. So we look at our first one, it's going to go from from 1 to 1.5. Next one's going to go from 1.5 to 2, then 2, 2.5, and then to 3. So you can see there's going to be 4 rectangles drawn there. So what we're going to have is 1/2 for our first rectangle, and since it's a left Riemann sum, my dot's going to look like that. And then at 1.5, be up a little bit higher, then up here, and then there we go. So that's about what the left Riemann sum would look like here. Definitely an under approximation. So the first rectangle is a half, that's the width. Now the height is determined by the point on the graph. Well, that's at 1. So I'm going to put f of 1 here, plus a half. So now for our second rectangle, it's still a half. And that its height is determined by the x value at 1.5. So you might do f of, I might like fractions. So 3/2. And then third rectangle, again, the width is a half, and the vertical distance is the height at 2. So f of 2, the y value 2. And then lastly, a half times f of 2.5. And the cool part here, kind of little shortcuts to help you along. We started at 1, the left endpoint, because we're using a left Riemann sum, and then the x's actually just went up by the width of our rectangle, half. So it went 1, 1.5, 2, 2.5, and the only number we left off is 3, because that's the right endpoint. So left endpoint, left Riemann sum, leave off the right endpoint. So our right Riemann sum is going to leave off actually the left endpoint. You'll see that here next. So I won't draw these all the time, and actually drawing them is really only for you, to make sure that you understand what it looks like. But once you've got it, you're good. So every rectangle is still a half, and you might want to draw these here. So our first one goes from 1 to 1.5. So that's the height of the first one, there's the height of the second, oops. The third one looks like this, and the last one up here looks like that. All right, so those rectangles are right endpoints, right Riemann sums. So when I do the first rectangle, it's a half times wherever the dot is. Well, the point on the curve is at 1.5, so it's f of 3/2. And as we predicted, we have left off 1, the left endpoint. Second rectangle is a half times f of 2, plus a third one, half of 2.5, and then a half times, f of 3. Okay, so, and actually each one of those f of 1, f of 2, f of 3, all these can actually be figured out because we have the function. So we'll be plugging those into the calculator to kind of find those easily, a little bit faster. So we'll give you a little bit of a tutorial how to do that quickly when we get back. So then finally the midpoint. Midpoint is, again, the ugly one, because now you have all these, and those are the subintervals. Sorry, your widths are all half, right? But you're going to go up at the midpoint of each of those. So halfway between 1.5 and 1 is 1.25 if you want to use decimals. So the width is still half. That does not change. But the height now is not determined by 1 or 1.5. It's determined by 1.25. So this one's between 1.5 and 2. So kind of right in the middle there, which would be 1.75. And again, if you want to find a faster way of doing this, the distance between 1.25 and 1.75 is still half. So if you do it that way, add a half to this, that's f of 2.25, plus another half of that is, 2.75. Okay, so that was that, and then, so this is all the setup. This would be something you would get points for on the AP test, so you do want to show this work. And then you can like put this all in the calculator with given this function and get the actual values of this. So one more thing to talk about is that was more with a function based. This is now with a table. So things change just a little bit here. This one is actually a velocity function that they give us of a train. And so there's their velocity over the first 10 seconds. Now this one says use a left Riemann sum with 10 subintervals to estimate the distance traveled. So distance traveled comes from position. So basically we want to integrate this velocity equation. So the thing I always do with tables, and I know, and especially with 10 subintervals here, it's kind of annoying, but one, that's the first rectangle, goes from 0 to 1, and then 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are all your rectangles kind of illustrated a little bit. So if you look at each one of these, its width, okay, that's like the x values, in this case time, is 1. So you can do 1 times. And the nice part is you don't have to write f of 0, f of 1, f of 2, because those are all given already. So for a left endpoint, if we're between 0 and 1, well, the point on the left would be 0. And so the second rectangle here, again, the width is still 1, and the left endpoint would be 12. And then you can go on and on and on with this. So times 22, 1 times 10, 1, oops, times 5. So you just, I mean, we can keep going and going and going here. That's the way that the left endpoint works with a table. So same thing here, the right Riemann sum. And you know what? I'm tired of writing 1 times 1 times 1 times. They're all 1 here. So what I'm gonna do is take a GCF out. Instead of having all these 1 times 1 times 1 times, I'm just gonna take 1 out and just add up all the heights. But the right Riemann sum, especially of our first rectangle here, is important. It's not 0 first, it's gonna be 12. And the next one's gonna be 22, and then 10, and then 5, and then 13, and da 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 da, and we're gonna end at 0. So that's that. Now, this is what makes these very interesting. So this last one, midpoint with 5 subintervals. So 5 subintervals from 0 to 10, it's going to have a kind of a width of a 2. So watch, this is what I think helps. That's 1, 2, 3, 4, 5. So there are your rectangles this time. And it'll make a lot of sense in a minute. Again, each one of their widths is 2. So if you want, you could take 2 out as a GCF. So 2 times for every one of them. And now the height, well, it's not at 0. That would be a left endpoint. At 2 would be a right endpoint. The midpoint's 12. So really, all these numbers in the middle are the only ones that we're going to use. And so we just add those up. And that would be the setup for a midpoint approximation. Again, you can quickly throw that in your calculator and get the actual numbers. All right, so then the last type of approximation is not using rectangles. It's using trapezoids. And it's actually kind of a cool way of doing it because it has this angle. The angle side follows a lot of the curves. So that'll be kind of something that makes it a little bit more accurate. All right, so we're gonna do these individually again. So if we're doing the same parabola we did before from 1 to 3. We're gonna divide that up 4 times. So again, it's a width of half. If you wanted to see that again, remember b minus a over n. So 3 minus 1 over 4 is a half. So this first one goes from 1 to 1.5, and it's a trapezoid, so it's kind of cool. You go up here at both of those endpoints and draw that. So, and you can see just by the drawing itself, that one's going to be a little bit better approximation. You're going to see slight over approximations there, but it's still a lot better than using rectangles. So to set this thing up, each rectangle, there's four, or sorry, each trapezoid, there's four of them, do individually. So the formula is right here if you really need it. So 1/2 times the height, base 1 plus base 2. Now the height is always the distance between the two parallel sides. I don't know if you remember that. So that's actually this. So the height is actually 1/2 for all the trapezoids. So we've got 1/2 times 1/2 here, and then base 1 plus base 2 is f of 1 plus f of 1.5. That's our first trapezoid because 1 here and 1.5 here. So that's f of 1 and f of 1.5. So plus, and our second one is going to be, again, bring down the 1/2. The height is 1/2. And now your base 1 and base 2 and this one are at f of 1.5 and f of 2. And that was done. And then your third one is 1/2 from the formula, oops, times 1/2 for the height. And then you've got, this one is f of 2 plus f of 2.5. And lastly, the fourth one is going to be 1/2 from the formula, 1/2 for the height. And now your two bases on this one are at 2.5 and 3. So f of 2.5 plus f of 3. Sorry, there on a space there. And again, each one of those can be figured out in your calculator. Here is your f, your function. And plugging in 1, 1.5, and you'll see that these numbers repeat themselves. So you don't have to plug in every single one of them. Once you find one, it'll help you out with the next one. So that's a trapezoidal rule, and you can see why we would use it. It's a little bit more accurate. So always look for what you're using, a rectangle or a trapezoid, how many there are. The interval is very important, and showing this step of all the work, you actually get points for that on the AP test. So make sure you do that as well. So feel free to watch this again if you need to. Use Remind if you have